Welcome back to another deep dive. Today, learner, we're dismantling an illusion.
A pretty big one, actually.
Yeah, usually when you think about computer chips, there is this expectation of absolute cold mathematical perfection. You picture a sterile, brightly lit factory, a grid of billions of microscopic transistors, and you just assume every single millimeter of that silicon is completely identical.
Right. It is incredibly comforting to think of the technology powering our lives as being built on this foundation of like flawless uniformity.
But it's an illusion.
It really is a pervasive illusion. I mean, we naturally want engineered systems to be symmetrical, to be perfectly balanced in every single direction. But the moment you zoom all the way down to the microscopic manufacturing level, that perfect grid just shatters. You find that we are actually dealing with a physical landscape that is heavily biased.
It has a grain to it.
Exactly.
And ignoring that grain has massive consequences. So that is our mission today. We are taking you into a highly technical yet incredibly consequential presentation from 2026 by an author known as Atlook036.
The title is Anisotropic Spatial Correlation Extraction via Gaussian Process Regression.
Which I know sounds like a massive mouthful.
It is a mouthful, yeah.
Yeah.
But what we are really looking at in this slide deck is a comprehensive guide to uncovering a specific microscopic asymmetry in how chips are actually made.
Right. And the slide deck essentially breaks down three things. First, the physical causes of these manufacturing quirks. Second, the advanced mathematical formulas engineers need to detect them. And third, a practical guide for fixing them.
Because if designers ignore this microscopic flaw, it can literally ruin the timing and the performance and the overall yield of the technology you use every single day.
Okay, let's unpack this. If the physical reality of the chip is somewhat warped, but our math assumes it's perfect, how much damage is that assumption actually doing?
Yeah.
To answer that, we have to start on the factory floor.
We do. Because before we can solve the math problem, we have to understand why this physical bias exists in the first place.
Right.
The core issue here boils down to two words: isotropic versus anisotropic.
Right. Let's define those for the listener.
So isotropic simply means having the same correlation, the same physical properties in all directions. Up, down, left, right, if you measure it, it looks identical.
But anisotropic means the properties change depending on the direction you are measuring. So the spatial correlation lengths in the x direction and the y direction are totally different.
Exactly.
To make this a bit more intuitive for you listening, think about mowing a lawn or maybe painting a wall with a roller. You can try your absolute hardest to make that grass perfectly uniform or that coat of paint perfectly smooth.
But you can't totally erase the process.
Right. The physical direction of your movement, like the path you walked with the mower or the up and down motion of the paint roller, inevitably leaves a distinct pattern. It leaves a grain.
If we connect this to the bigger picture in chip manufacturing, this grain comes from two main physical culprits during the fabrication process. The first is the lithography scan direction.
Lithography is essentially the process of projecting incredibly complex microscopic patterns onto the silicon using light right.
Yeah, and the machine that does this, the scanner, physically moves along a specific path, the axis. Because it's scanning in that direction, any tiny vibration or variation gets stretched along that path, creating a longer spatial correlation along the axis.
It's like taking a panoramic photo on your phone while moving your hand.
Yes, exactly.
The blur or the stretch happens entirely in the direction you are panning. And the sources note that this scanning motion specifically affects something called the gate critical dimension.
Right.
But let's pause there because we need to explain how a slightly stretched gate actually impacts the computer. How does a physical shape change a digital outcome?
Well, it comes down to basic electrical physics, specifically resistance and capacitance. A transistor gate is basically a valve for electricity. If the lithography scanner makes that gate slightly wider or narrower along its path, you change the capacitance of that valve.
Oh, wow.
Yeah, it takes a tiny fraction of a nanosecond, longer or shorter, to fill up with electrons and switch on.
Which is everything at that scale. And the second culprit the presentation points out is CMP, or chemical mechanical planarization. This is basically the polishing phase.
Right. They essentially take a giant spinning pad and an abrasive chemical slurry and grind the top of the wafer perfectly flat.
But the machines polish the wafer in a way that is direction dependent. It creates directional variability along the x-axis.
Because the material removal rate actually changes based on how dense the underlying pattern is.
Yeah.
If you have a cluster of metal lines next to a wide open empty space, the polishing pad bends slightly and removes material unevenly.
Okay, so this alters the thickness of the metal interconnects. the tiny copper wires connecting the transistors,
Exactly.
which again alters the physics. Thicker metal means less electrical resistance. Thinner metal means more resistance. So the timing of the electrical signals across the wafer is fundamentally altered.
The chip literally behaves differently depending on which way the electrical current is traveling, as a grain.
Which brings us to the real danger. Now that we understand these chips have a physical bias, like a longer correlation in the Y direction from the scanner and variability in the X direction from the polisher, we have to look at the models engineers use to design these chips.
And the presentation gives us a major spoiler right up front. Engineers often use an optimizer model that assumes an isotropic, perfectly uniform correlation.
They assume the chip is a perfect uniform square, even though the physical reality is a stretched out rectangle.
Right. And when the math encounters a rectangle, but is only programmed to understand squares, the optimizer tries to force a compromise.
A compromise.
Yeah, it looks at the longer correlation in the Y direction and the shorter correlation in the X direction, and it tries to find a single average length scale, which is represented mathematically by the letter L.
Okay, wait, I want to push back on this for a second because in almost every other field of engineering, a compromise is a good thing, right? You find a middle ground to balance competing variables. Why is finding a compromise length here the worst possible outcome for a chip designer?
In many fields, a compromise is a safe bet, sure. But here, a mathematical compromise provides a highly dangerous false sense of security. The middle ground isn't real. It physically does not exist on the wafer.
Oh, okay.
By picking a number in the middle, the model systematically underestimates the correlation in one direction and overestimates it in the other.
Oh, I see. You're effectively blinding yourself to the true terrain.
Exactly. The design becomes non-optimal in both axes simultaneously. Let's say in the Y direction, the properties vary very slowly. But your compromise model assumes they vary quickly. Your design is now overly conservative, wasting power or space to protect against a variation that isn't even there.
And in the X direction, it's the opposite. The model is overly optimistic. It assumes the chip is more uniform than it really is.
Which is a disaster.
What's the absolute worst case scenario there?
Well, you calculate your timing margins, the microscopic fractions of a second. A signal needs to travel from point A to point B based on this phantom middle ground. You manufacture millions of these chips, and when you turn them on, the signals arrive too late or too early because the physical resistance and capacitance were completely different than your model predicted.
Oh, man.
The chip fails its specifications. You faced total yield loss.
Yeah.
You end up throwing away millions of dollars of silicon because your mathematical compromise lied to you.
That is genuinely terrifying. You're building hyper-advanced technology based on an average that physically does not exist. So if forcing a rectangle into a square ruins our yields, how do we upgrade the math? How do we build a model that actually understands the grain?
This is where the presentation moves us to a four-parameter model using Gaussian process regression.
Now, Gaussian process regression is basically an incredibly advanced way of predicting the unknown based on the known right.
Exactly. If you measure the thickness of a chip at point A and the thickness at point B, Gaussian process regression helps you guess the thickness of every point in between based on spatial correlation.
And the original isotropic model only tracked three things:
Right.
the single length scale, the overall variance, and the random noise.
Right, but the new anisotropic model tracks four: the length scale specifically in the X direction, the length scale specifically in the A direction, the variance, and the noise.
To do this, they use mathematical engines called kernels. And the sources specifically mention the Gaussian kernel and the Matern kernel, like the Matern 3/2 or Matern 5/2.
Is kernels are the key here.
Let me jump in with an analogy for what a kernel actually is for you listening. Think of a kernel like a rule book for guessing the temperature in a room. If you were standing next to a hot radiator, you can safely assume that a spot 2 inches away is also hot. That is high spatial correlation. But a spot 10 feet away by a drafty window, the radiator tells you nothing about that spot. The kernel is the specific mathematical formula that dictates exactly how fast that correlation decays over distance.
That is a perfect way to visualize it. And the reason the presentation mentions different types of kernels is that real-world manufacturing data isn't always perfectly smooth.
Right.
A Gaussian kernel assumes the physical variations are infinitely smooth and gentle like rolling hills. But Matern kernels are designed to handle rougher, more abrupt changes in the data. They are much better suited for the harsh physical realities of, say, polishing metal on a wafer.
Here's where it gets really interesting, though. I'm looking at this 4-parameter upgrade and something doesn't track. You would naturally think that tracking more variables, adding completely independent x and y dimensions to a complex optimization, would make the math incredibly sluggish.
Oh, absolutely. In the world of machine learning and modeling, adding dimensions usually grinds computers to a halt. The computational load just explodes.
Right, the curse of dimensionality, that is usually the brick wall you hit. So, why does the author claim this anisotropic model is highly efficient?
The brilliance relies on a concept called a separable kernel structure. The anisotropic kernel isn't just one giant tangled four-dimensional equation. It factorizes,
Okay, what does that mean in practice?
meaning the mathematical formula for the 2D plane can be split cleanly into completely independent x and y components.
So instead of the computer trying to solve a massive unified grid, which requires exponentially more memory, it just solves a line in the x direction and a separate line in the y direction and multiplies them.
You've got it. Breaking the matrix math into smaller independent pieces is what allows the computer to process this extra dimension without breaking a sweat. It is a deeply elegant mathematical solution.
Okay, so the theory is beautiful. We have a separable four-parameter Gaussian process that can detect different stretch marks in the x and y axes. But having a brilliant theory is one thing. Proving it actually works on real-world manufacturing data is another. How did the author verify this?
Well, you can't just test a brand new algorithm on a real physical chip right away.
Right, because a real chip is full of unknown microscopic flaws. If you run your new algorithm on a real chip and it spits out a pattern, you have no way of knowing if your algorithm found a genuine spatial correlation or if it's just hallucinating patterns in random noise.
Exactly. To prove an algorithm works, you need absolute ground truth data. You need an answer key.
And to get that answer key, the presentation details a rigorous methodology where they had to reverse engineer the problem using a technique called Cholesky decomposition.
Yes, Cholesky decomposition is a matrix math operation that allows you to do the exact reverse of the extraction problem. Instead of looking at a chip and trying to find the hidden pattern, you start with completely independent, uncorrelated white noise.
Okay.
Then you use Cholesky decomposition as a filter. You mathematically force that random noise into correlated samples based on an anisotropic kernel with parameters you have specifically chosen.
I absolutely love this methodology. It's like you are drawing a highly specific treasure map, wiping your own memory of what you drew, and then testing if your brand new map reading software can recreate the exact map from scratch.
That's exactly it.
You build a perfectly flawed simulated chip. You dictate exactly how strong the grain is in the X and Y directions just to see if your algorithm can diagnose the exact flaws you purposefully programmed into it.
And the author notes exactly why Cholesky decomposition was the right tool for this specific test. For their test case of about 80 observation sites on the simulated wafer, Cholesky is perfectly exact and highly reliable. But there is a catch. It has a computational cost that scales cubically.
The source mentions ON cubed. Let's unpack what that actually means for a listener.
When mathematicians say something is ON cubed, they're describing how fast the computational time blows up as you add more data. It means if you double the amount of data points you are analyzing, the time it takes, the computer to solve the problem doesn't just double.
Right.
It multiplies by 8. If you triple the data, it takes 27 times longer.
So if you have 10 data points, it might take 1,000 operations. But 20 data points takes 8,000. It gets incredibly heavy, incredibly fast.
Which is why Cholesky decomposition is perfect for a controlled simulation of 80 sites. But you would never use it to directly analyze millions of transistors at once.
Even with just 80 sites, the simulation had a major hurdle. The presentation highlights something called the Optimization Landscape Challenge. Because the algorithm is now searching for answers in a four-dimensional space instead of a three-dimensional space, there is a very real risk of what the author calls parameter swapping.
This is a fascinating quirk of multidimensional optimization. The algorithm is basically walking blindfolded across a hilly landscape, trying to find the lowest valley, the mathematical point of lowest error. But because it's looking at both the x-length and the y-length, it can accidentally mix up the labels.
Oh, I see.
Yeah, it might find the right measurements, but assign the scanner's y-axis correlation to the polisher's x-axis.
Because to the computer, a rectangle rotated 90 degrees looks mathematically identical.
The algorithm gets stuck in what we call a local minimum. It thinks it has the perfect answer, but it simply swapped the variables. To prevent this, the author had to build in safety rails using a multi-start approach. Multi-start, right. Instead of dropping the algorithm into the landscape once they ran the optimization with 12 or more completely random starting positions, This ensures the algorithm explores the entire 4D space and settles on the absolute true values rather than getting tricked by a swapped parameter.
Okay, the methodology is incredibly solid. The theory is sound truth. The ground truth simulations are built using Cholesky decomposition, and the safety rails are in place with multi-start optimization. What were the actual results? What is the payoff for the engineering world?
The extraction accuracy of the new algorithm was staggering. When they ran the simulations with a sample size of 200 data points, both the X and Y correlation lengths were recovered with less than 1% error when using the Gaussian and Matern kernels.
Less than 1%.
Yeah. Even with an exponential kernel, the error was only around 3 to 5%. The algorithm successfully found the hidden grain almost perfectly.
But there is a catch regarding that sample size. Because we upgraded the math to track 4 parameters instead of 3, the algorithm is hungrier. It needs a lot more data to confidently lock onto the truth.
The data explicitly shows that you cannot do this on just a handful of test measurements. 200 or more samples per wafer is excellent for resolving the anisotropy.
Okay.
100 samples is considered good, though you start to see slight degradation in accuracy. But if you drop under 20 samples, the performance is rated as poor. The math just starves. It doesn't have enough data points to reliably separate the X direction from the A direction.
Which naturally leads into the most crucial part of the presentation, the practical guide. The author doesn't just drop this heavy math and walk away. They give engineers a highly actionable ratio test to determine when they actually need to use this 4-parameter model.
It is wonderfully straightforward.
It really is. You take your maximum correlation length, let's say the y-axis from the lithography scanner, and divide it by your minimum correlation length, the x-axis from the polisher.
And that simple ratio dictates your entire modeling strategy. The author outlines clear golden rules. If the ratio is under 1.5, the grain of the chip is so minor that the traditional simple isotropic model is perfectly fine. You don't need the computational heavy lifting of the 4-parameter model.
But if the ratio is between 1.5 and 3.0, you have moderate anisotropy.
Right. And if that ratio is greater than 2, the source sends up a massive red flag. Sticking with the isotropic perfectly square model will introduce significant critical error into your timing margins.
And anything over 3.0 means strong anisotropy. You absolutely must use the Gaussian process regression upgrade, or your yield will suffer catastrophically.
They also provide guidance on matching the mathematical tool to the physical reality. If your dominant manufacturing issue is the lithography scan, where the axis stretches much longer, they recommend using the Matern 3/2 kernel.
And if the dominant issue is the CMP polishing, where the x-axis variability dominates due to pattern density, they recommend the Matern 5/2 kernel.
Exactly.
So what does this all mean? I want to focus on the ultimate takeaway the presentation drives home for the listener. The source explicitly advises engineers to never just guess and to never blindly trust a single model.
Yeah. The author says you should always fit both the isotropic and the anisotropic models. Run your data through both, compare their log likelihoods, and let the data tell you the truth.
Let's unpack log likelihood for a second. The log likelihood is effectively a scoring system, right?
Think of it like a courtroom where the physical data is the judge.
Yeah.
You present the isotropic model, which says the chip is a perfect square.
Mm-hmm.
And you present the anisotropic model, which says the chip is a rectangle.
Right.
The log likelihood is the mathematical score of how probable it is that the physical data was generated by that specific model. By comparing the scores, you let the math reveal if your chip truly has a grain rather than making an assumption.
It is a masterclass in letting evidence lead design. If we retrace the journey we've taken today, we started by recognizing that physical constraints on the factory floor, the literal direction a scanner moves or a machine polishes a silicon wafer, create microscopic directional biases. Anisotropy.
And we saw how ignoring that physical bias and assuming absolute uniformity leads to a phantom mathematical compromise that ruins chip yields.
We explored how upgrading to a separable 4-parameter Gaussian process regression model fixes this. And we saw how the author rigorously verified that algorithm by reverse engineering ground truth data, with Cholesky decomposition ensuring it could find the hidden grain with less than 1% error.
This deep dive into a highly technical 2026 slide deck isn't just a lesson about microchips. It is a profound demonstration of how the tools and models we use dictate the reality we are able to see.
If you use a simplistic model, you will get a dangerous compromise. You will be completely blind to the actual terrain you are trying to navigate. The tools dictate the reality we see. It leaves you with something pretty wild to mull over. If our highly controlled, hypersterile, microscopic chip manufacturing processes, literally some of the most precise engineering environments on Earth, are fundamentally anisotropic and full of hidden directional biases, what other complex systems in our daily lives are we incorrectly treating as perfectly symmetrical?
It's a great question.
Are we using simplistic isotropic math to model traffic patterns or financial markets or even the spread of information on social networks just because forcing a rectangle into a square is easier to swallow? Next time you assume the world is a perfectly uniform grid, remember to check for the grain.